hold on a second.
Problem 23.02.
Okay, this is the sample problem 2302 for Gauss law. So let me show you this video and a couple of, sample problems. I'll just then move on to the next chapter. So
the closed Gaussian cube. A non-uniform electric field given by E 3xi plus 4j pierces the Gaussian cube shown in the video 23-7a, the one on the right. E is in newtons per coulomb and x is in meters. So question is, what is the electric flux through the right phase, the left phase, and the top phase? We consider the other phases in another sample problem. Actually, that problem is, what is the net charge enclosed by the Gaussian cube of sample problem 2302? So now let's take a look at the picture. So the electric field already exists in the space that pointing at right upward, as you can see here. So that electric field can be decomposed into x components in the x-axis, the one in the y-axis. So that electric field passing through this Gaussian cube, like this, and you can actually calculate the quantity of electric flux by integrating the electric field times the area vector on x, y, z basis. In order to start estimate the quantity of electric flux, first step might be to set up the area vector. Normally, area vector is defined by the vector is perpendicular to the surface of Gaussian cube or Gaussian surface. So here, A vector A is the area vector, and that is normally perpendicular to Gaussian. It's Gaussian surface. So if you look at the picture B, that the arrow indicates the direction of the area vector on the faces of this Gaussian cube. So there's 3 bases, the 6 bases. So there are 6 different vectors aligned in the x, y, z axes. So if you look at small area segment on that base, then that area segments can be defined by dA, that is area element, which is small fraction of this base of Gaussian surfaces. So that is the area vector element, area vector element. And this dA vector could be defined by unit vector. So the question is we have to find the flux of electric field on the right base, which is aligned with the x-axis. So dA, in that case, the dA vector, the area vector element, is expressed with the scalar quantity of the area vector times unit vector I. So I vector is on the x-axis. So this dA vector, the face area vector, is aligned in the positive x-axis. So using that area vector, we can estimate the flux density and the flux of electric field along the right face of this Gaussian surfaces. So for the surface on the positive x-axis is given by this definition that the flux elements is expressed with the E by R. That is the electric field out of this vector quantity of field on that spot, pointing the right upward times area vector dA. So that is the flux quantity passing through the small area of dA on that base. So now next step is to estimate total flux out of that surface. So that is integral of, so let me rewrite it. So that flux, electric flux out of right base is integral of E by R. Then that you replace that with the electric field expression, then that integral of electric field dot product dA. Now let's replace electric field and the area vector with their given condition. So that is integral of the 3xi plus 4j dot product the ai. So that vectorial expressions can be converted into dot product of normal vectors. So that is integral of dx times dA first, and times I vector dot product I vector plus integral of the 4 dA times I cross product and dot product j. So as you know, the I, j, k are normal to each other, which means their unit vectors are perpendicular to each other. In the case of the dot products between the two vectors on normal direction lead to the zero vector, so that I dot product of j should be equal to 0. So only leave that this one. And dot product of unit vector itself, that should be equal to 1. So this lead to the answer of integral of 3x dA. So and you can see 3x is constant value that could be out of integral, because the x in this base of this cube, x is the 3 meter everywhere. So x value usually is not varying over surface. So that can be out of the integral. So if you take that into account, then 3x could be out of the integral, then you have dA. So that is area of this base of this Gaussian cube. So that this one is area of the right base of this Gaussian cube, which is this one side of this cube is 2 meter. So total area of this base is 4 meter square. So you multiply that, you got to times 3 times 3 meter times integral of that is 4 meter square. Then that is 36 36 Newton meter square over C. Okay, that is flux of the that phase of the Gaussian surfaces with Gaussian Q. And now with that idea, let's just estimate the flux on the left side, the left face and the top face too. So for the left face, everything is same, pretty much the same procedure we need to take, but some of the variable like x should be different. So here in the left face, x, as you already saw, is 1 meter. And also dA should be divided with the negative direction, so that should be minus dA I. Now you want to just do the same estimate. So the flux on the left face is integral of electric field dot product of dA. So if you plug all those expression of electric field and area vector, and that should be minus 3x integral dA. So here, this one again is 4 meter squared, and then x is 1 meter this time. So that is minus 12 Newton meter squared per coulomb. Now let's just estimate the flux on the top face. So top face. Now top face like this, right? And then that is pointing upward. So area vector dA point upward, so that dA can be expressed with the magnitude of area vector times J unit vector. So with that quantity, the flux on the top face can be expressed with the integral of 3x I plus 4j dot product dAj. So that is integral of 3x I dot product j plus integral, here should be a too, integral of 4 dA j dot product j. So this I product j equals 0, and I product and j product j is equal to 1. So that only leaves 4 integral of 4 dA. So the 4 could be out of integral as is that's just number. So here integral dA is area of top surface, which is still 4 meter square. So total flux out of that surface, I mean the base of the Gaussian cube is 16 Newton meter square over coulomb. Second question is, what is the net charge enclosed by the Gaussian cube of sample problem 3.02? So based on the Gauss law, the net charge inside includes Gaussian cube or Gaussian surfaces could be given by the total integral of the electric field over the total surface of Gaussian cube. So in this case, we have to first estimate the electric field integrated by the surface area or face of size of the Gaussian cube first. That should be equivalent to a total charge inside of this Gaussian cube. So we already estimate the flux of 3 surfaces, left, right, top, and the next one, then we should actually come up with the numbers of electric field, total electric field times surface area, and on the other 3 actually bases. So for the bottom face, next step, for bottom face, the bottom face is which is the on the negative y-axis, and the area vector is that should be minus dA j in the y-axis. So if you plug that into total flux cross or through that, the bottom base is interval of electric field dot dA. From that, that should be minus 3xi and then j 4j dA j, right? So from that, just like the electric field flux on top surface, total amount of actually the flux should be same as the one on the top face, but with a negative side. So that should be 16 Newton meter square per coulomb. Then the remaining phases on this Gaussian tube, is the front and back faces, the front or back sides. So we can define first area vectors out of those two bases. So for front and back bases, the area vector element is given by this definition. The positive g-axis, that should be the AK, negative basis, and that should be minus the AK. But as you know, dot product of two normal vector is equal to 0. So that leads to the flux through those two bases out of electric field and area vector must be 0 out of these two normal vector dot products. So from that, total net flux through 6 bases of or 6 sides of this Gaussian cube should be given by 6 numbers: 36 Newton per Newton meter per unit Newton meter square per cube per coulomb, and minus 12 plus 16 minus 16 plus 0 plus 0 Newton meter square per coulomb. So this is that is right. This is the left. This is the top. This is bottom. And this one is front. This one is back. So all 6 sides of this cube is calculated based on the definition of the flux, electric flux. So from that, total flux out of this Gaussian cube surface is 24 Newton meter square per coulomb. Now we have to apply the Gauss law to estimate net quantity of the net charge inside of this Gaussian cube. So that is basically electric permittivity times flux is same as net charge inside of this Gaussian cube. So we have to multiply the net, and C is epsilon 8.85 times 10 to the minus 12 coulomb squared per Newton per meter square, and yep, you have the total flux is 24 Newton meter squared per coulomb. From that, net charge inside of this Gaussian cube should be 2.1 times 10 to the minus 10 Cool.
Okay, do you have any question about this problem and solutions? I think pretty straightforward. You just need to actually just integrate the surface with electric field Gaussian surface. Okay, then next example is about the shell shape. Now you have to estimate the flux across that the inner shell and outer shell. Take a look.
Sample problem 23 or 3. The figure 23-10A, the one on the right shows cross section. Plastic spherical shell with a uniform charge Q minus 16E and the radius R 10 centimeter. Particle with a charge of 5E is at the center. What is the electric field at point P1 and the radial distance 6 centimeter and the point P2 at radial distance 12 centimeter? So basically, this is a typical problem using the Gauss law. So you have a point charge, which is a source of electric field that either just radially just create electric field outward, or if in the case of the minus charge, then the electric field is just, converts into this point charge as a sink. So in order to actually estimate the net charge across the Gaussian surface, you first have to set up the Gaussian sphere. In this case, point charge is sitting on the center of system. So your Gaussian surface must be the symmetrical shape, which is a sphere. So the first step for first question, you have to create this Gaussian sphere inside of this spherical shell, because point 1 is inside the spherical shell. In that case, the electric field pointing outward, because the point charge at the center is positively charged, so that produces electric field outward. And spherical shell, inside the spherical shell, at the position the P1, the Gaussian surface should be like this. With the radial R. So with that idea, the R1 up to the point P1 has this kind of configuration. So this R1 is the radius of Gaussian sphere. And as I said, because this point charge Q is positive charge, the electric field is outward. And on the surface of this Gaussian sphere, areal vector is pointing outward. So with that, area vector element, it should be radially outward always. It must be always outward from Gaussian surface. So as long as you have Gaussian surface, you're sitting on surface, that area vector should pointing outward. So and then here the angle between electric field. So because of that, angle between the electric field and the area vector equals 0, because they are pointing the same direction. They all align outward radially. So theta, angle between the electric field from point the positive charge and area vector dA equals 0. From that condition, the Gauss law provides total quantity of net charge inside the enclosed area. So that is like this. So that's epsilon naught times electric field. Now dot product could be expressed with the cosine theta. So that is cosine theta dA. Here theta equals 0, so that is equal to 1. So from that, electric field, this given condition is constant value, so that could be out of this interval. So the interval of dA is same as surface area of a sphere, which is 4 pi epsilon r squared, radius of sphere. So there's actually epsilon naught. So that is same as net charge inside the Gaussian surface. From that, electric field could be expressed with this notation, and Q point charge divided by 4 pi epsilon r squared. That is electric field inside the shell. Now let's take a look at the electric field outside the shell. If you stay out of the shell, because this shell negatively charged, electric field should be inward. And now the area vector, as I said, on the Gaussian surface always outward. So angle between electric field and area vector is 180 degrees. So if you use that condition, number 2, if electric field at point 2 outside of the shell, so total quantity is like net charge inside of this Gaussian sphere include point charge Q and shell of this sphere. So that is Q plus F dot Q. Now his small q is 5e, and the shell is charged to minus 16e. From that, total charge inside of this spherical shell is minus 11e. By the way, that when this radius of Gaussian sphere is smaller than the spherical shell, then this Gaussian sphere only include the point charge in that enclosure, so that Q value should be 5e. So that is same as 5e 4 pi epsilon naught r squared. So then now we have this one inside of this interval. So the electric field is minus Q. Let me just fully express that. So the epsilon interval flux electric field EA will be same as Q, E, and C. And from that, this one should be electric field for, so that right now, that is interval of electric field cosine theta dA. Your theta is 180 degrees. So that should be minus interval electric field dA. Here, electric field still constant value inward. So that should be minus electric field interval dA. And this one is 4 pi r squared. So you plug that, then total amount of net charge is minus epsilon electric field 4 pi r squared is Q net charge inside of the Gaussian sphere. So electric field outside of the shell should be minus Q, E, and C enclosed 4 pi epsilon naught r squared. So as I said, this Q, the net charge inside of the Gaussian sphere includes point charge Q and small q, and the charge of the spherical shell, which is 11e, the 60 minus 16e, so total charge minus 11e. So that is minus 11e over 4 pi epsilon naught r squared. So the minus sign cancel each other. That leaves 11e times 4 pi epsilon r squared. So number one, if you stay inside the shell that contains point charge in the spherical radius of Gaussian sphere, that electric field is the 5, let me just rewrite it, 5 times E 4 pi epsilon naught r squared inside at P1. Now we plug that all the value inside of this formula, then actually 5 times E 1.6 times 10 to the minus 19 colon divided by 4 pi 8.85 times 10 to minus 12 colon square per Newton per meter square. And the radius of the point 1 P1 is 6 centimeters, 0.06 meter square. You plug them all, then that lead to the electric field of 2 times 10 to the minus 6 Newton per coulomb. And now, second question, electric field is 11E over 4 pi epsilon naught r squared. This is outside the shell at P2. Plug that 11 times 1.6 times 10 to the minus 19 coulomb divided by 4 pi 8.85 times 10 to the minus 12 coulomb square per Newton per meter square divided by the point 2 is the 12 centimeter apart from the center of the sphere, so that is 0.12 meter square. So from that, electric field at point 2, P2 is 1.1 times 10 to the 6 Newton per coulomb. Okay, that is answer for 23.3.
So, okay, before moving on to the next one, any question about this question?
So when it's outside of the out of like the what is it called? The shell,
Mhm.
have to factor in the cosine theta, which is equal to 180. So
Mhm.
then even if it's a negative, it turns into a positive value.
The reason you have 180 degrees because the shell is negatively charged, right? So that the flux line, electric field, inward actually to the shell. So your Gaussian surface, you look at Gaussian surface itself is outside of the shell. So if you're standing on the surface of the Gaussian sphere, then the field is outward, but the field is inward, but your area vector, dA, is outward. So two vectors are the opposite direction. So that's why you have end up with the 180 degree in theta, the cosine. If you stay inside of, if you that the charge inside the Gaussian surface is positively charged, then that field is outward and your area vector is also outward. So they are pointing the same direction in radial direction. In that case, theta is equal to 0 because the two vectors is pointing the same direction. But now the shell is negatively charged. The field is inward. Area vector is outward. So they are just opposite direction. Does it make sense? Okay. Any other questions? Okay. All right. And I'm going to skip the 23.7. That is just hold on a second. Let me open up. So I think we actually already just reviewed this similar problem before. So you have like two parallel plates. Then if you just add the electric field from the positively charged plate at the left side of this plate, and the field from the negatively charged plate, then if those two plates are equally actually charged, then the field at left-hand side of this positively charged plate is going to be 0. Same thing for the right-hand side of this negatively charged plate, also have the 0 field, and only leave that inside of this parallel plate has positive field, finite number of quantity of electric field. So that's basically the basic idea of capacitor. So you said you learn about the capacitor in your school, right? So capacitor is normally have electric field only inside of these kind of two parallel plate, but the amount of charge accumulated inside the capacitor is pretty much depend on the relative permittivity inside the parallel plate.